Thanks to the organizers of this conference. This is a very interesting conference, my first time at the Technion, and it feels really, my hat's off to the organizers. It feels like a family affair, really makes everybody comfortable, so that's wonderful. The big takeaway from the presentation today, I'm going to focus on one particular area of where we want to make, of how we want to make verification easier and simpler. The takeaway is how you can steal ideas from a neighboring domain and actually apply it somewhere else and create innovative processes and innovative tasks this way. When I talk about verification, and this is the lingo we are using at IBM and many other companies. I learned yesterday from Andreas, this is actually practical verification. So it's actually testing and verification. I'll show you a little bit of the context here. But let's get going. I first need to give you, before I can describe the real problem that we're solving with aspect-oriented design, I need to give you some context, and for that purpose, I will talk a little bit about chip design principles for the software people around here, which I think we have plenty, and also give you an example of a system on a chip, a typical one, a typical large one that's representative for like the state of the art in the industry of large designs. And then I want to go to the core of the problem statement, which is saying that we have constraints in the logic design of these systems on a chip that really violate modularity boundaries and modularity itself. And the drawback of this is that we actually then suffer in verification, and we have to overcome those constraints. And this then leads to this idea of aspect-oriented design that we've created in the last 2-3 years. So just from a very first principle standpoint, what we're doing with these designs is we start from an architecture specification. IBM happens to have two instruction set architectures. The examples I'm using come from the Power architecture, which originates from the RISC workstation projects in the 90s. We also have the mainframe architecture. The design process is the same for both, just two different brands, two different application areas for the systems we create. Typically, the micro-architects take this, with every iteration of these chips, they take the architecture specification and create a new blueprint of how the machine actually solves the problem of implementing the instruction set architecture. The logic design team, and now we're talking about easily on the order of 100 people or more. So this is few people up here. We come down here, we have larger teams. They use a high-level language to specify the implementation of the microarchitecture. And then we go in parallel, we have two efforts going on. There's the circuit implementation, which actually maps this logical specification into physics. And on the other side, we verification guys, we take this a model of this design. This is typically a compiled version of this high-level language specification of the logic, and we run our verification strategies around this design model exclusively. Now, the first place where formal verification is, in this case, this is then true to the word verification, comes into play is that regardless whether the circuit implementation is manual or whether it is via what's called in the industry logic synthesis. Prior titles for this was silicon compilation. So the automation here, regardless whether it's manual or not, we need to close the gap between the design model and the circuit implementation, because we're spending a lot of effort in the verification strategies, and we have to make sure that we're actually really verifying what we're building ultimately. The goal is to find more than 98% of the bugs in pre-silicon. Now, about 10 years ago, I was on a panel in Europe somewhere, and I was almost chased off the stage because they said, "You wimp, you're saying 98%. What about the remaining 2% there? What are you? You're giving up before you even declared what the goal is." The reason this is the case is verification of these large designs is really an untractable problem. So if you face the reality that says you will find 1 or 2% of the overall bugs that you find during the development process in post-silicon that changes your behavior drastically, that actually changes your design drastically. And in the end, it doesn't really matter that you find bugs in post-silicon there, in the actual bring-up lab when the first generation of the chips come back, as long as the total life cycle of the project is optimized for time. So time is of the essence, the time to market in this case, and if you calculate the 1 to 2% in, you actually create a more efficient process overall. So this is just to give people that have never seen this a little bit of a flavor of how these high-level design languages look like. The typical languages that are used in the industry are called VHDL and Verilog. There's the derivatives and follow-ons to especially Verilog. Doesn't really matter. But the main thing you should have seen before we go into more detail of this is that all these languages have in common that they have a structural component which actually allows people to define modules, subcomponents that go on a chip like this with their inputs and their outputs, and since you have modules there has to be an instantiation hierarchy. Now this is what you see here roughly. I'm not going to go obviously in syntax details, and then the blue stuff is actually the behavioral of this particular block that implements the function that the designer has in mind, that takes the inputs and updates the internal state that this module has and generates new outputs. So we call these languages and this style of coding RTL, and I will use this, therefore I had to specify this a little bit better for people that are not familiar with hardware design. RTL stands for Register Transfer Level. Sounds complicated, it's very simple. All it says is that the function is defined in a state machine, finite state machine type fashion. The output and the state elements, the registers of this particular module at the next clock cycle, that's the n+1 here, is defined as a function of the inputs and the registers at the current state. So it's simple state machine update kind of operation. Now the trick with this type of design style is that this has to be mapped in the implementation as efficiently as possible to two-dimensional, sometimes three-dimensional geometries, and implemented in such a way that it fits on a chip and that it can be clocked at the highest speed rate that defines the product. So what we do in verification, and as you look across the industry, you see these wildly differing ranges of numbers that define how much is design verification actually the part of the overall project time. What you see is that between 30 and 70% of the overall cost of doing one of these chips, one of these systems, is verification. Widely depends on how much reuse there is, whether it's in the 30% or in the 70% range, but it is a dominating factor. So verification is a very big problem in defining and designing new systems. All we do in verification is we drive tests against the design model and we check them, and then we track coverage. And based on the coverage we achieve, so that's pretty plain vanilla, we adjust the test strategy and go on and try to find our bugs. So bug hunting is the majority of the purpose of this type of verification. We have different engines on which we run verification, and they're listed here. They have all different characteristics, and so what we try to create in design verification is really this patchwork of overlapping but non-redundant approaches to find all the hardware bugs, or at least the 98-point-something% of the hardware bugs before we get to silicon. But since we accept that we find some, hardware bring-up is actually part of the first generation of hardware bring-up, is part of the verification process. Some of the very, very expensively hard to find bugs that would be expensive either in formal verification or even in hardware accelerated simulation, we catch then in hardware bring up. So those are the 4 platforms we use in this space. So we do this hierarchically, as you would expect. as the software disciplines have taken that approach, at least in some areas as well. So with clearly defined module interfaces and clearly defined module functions, this verification task becomes more efficient. And we do a lot of this at the module level, at the level of smaller modules, because you have more controllability and better observability to find those bugs. But over time, we go up this design hierarchy, and ultimately, at some point, we're trying to test the whole system, typically in simulation. This is an example of one of our latest designs. It's called Power 8. So it's the 8th generation of the Power ISA architecture. This is a 12-core chip that has 8 simultaneous threads. Has a bunch of attributes that you can read really quickly. Probably not all too surprising. Has a number of large caches for performance. And probably the most notable new things are that because the scaling of frequency has really come to a halt, we're moving performance features more and more into specialized hardware, and this would be the creation of these accelerators for crypto, for memory expansion, transactional memory, things like this. Or on the bus interfaces, we have this new interface that I'll describe a little bit more in detail to connect dots from yesterday when the SAP presentation talked about GPUs and FPGAs. I want to show what we're doing in this space here, just to show how in the real world these types of trends in the industry actually define the design process going forward. So we're working on Power 9 right now. One of the things that you always see going from generation to generation is that the resilience, the amount of investment done in resilience of the design is actually enhanced all the time. So reliability plus means there's a lot of features in this machine that prevent the customer from ever seeing hardware fails or hardware disturbances. As we saw from Bianca yesterday, soft errors, for example, is one of those potential problems, and she was talking about that in the DIMM space. The soft errors also occur on the chip itself, and so there's actually hardware support to deal with this preventatively and actually not have the end user, which is the program running on the core, ever experience that there was such a bug. This was also mentioned in the SAP presentation. We created a collaboration around an organization that we call Open Power, that has founding members from IBM, Tyan, Google, Mellanox, and NVIDIA. Those are the core members. The sorting here of the icons is done on purpose based on how close to the hardware the collaboration actually goes. So you see it goes from the chip SoC level, where we have now a Chinese company called Suzhou Power Core that's taking the Power 8 design and creating derivatives. So they go all the way down to the chip itself. We go to boards and systems, where Tyan would typically be IBM themselves, of course, and further up the stack all the way into the software space where companies come together. This collaboration is clearly a reflection and a realization that innovation is less in the pure hardware going forward, but it really needs the synergy of all these different components coming together that also drive the hardware still to make the next steps in performance going forward. So I promised we'd talk a little bit about our Coherent Accelerator interface, which was the door opener for a lot of these collaborations. So what we did here, don't get fooled by this PCIe label here. This is just a transport protocol, but what we did is we really allow now a coherent, meaning to the coherent processor bus, an access from FPGAs or GPUs. What this allows people to do is basically put applications either on the GPU or on an FPGA and connect them directly to the coherency fabric, which means they can access the same address space as any core in the system does. So it sort of opens up the inner sanctum of an SMP system that a piece of customer-defined hardware now, or in the case of a GPU, an algorithm on a GPU, can participate very directly in accessing memory in the coherent space of the machine. So from an application standpoint, the way this looks like is the application sets up running on the core, on the processor core, on the actual chip. It sets up the data in memory and calls one of these AFUs, which are on an FPGA, to do the specific acceleration work. That could be a Monte Carlo algorithm, that could be a sort algorithm, that could be any compute-intensive algorithm that we also saw yesterday that is put out there. And then the AFU in hardware speed reads and writes the coherent data across the system bus, so it has directly access to the memory space that the core application also has, without going through any amount of hoops or indirection. When you compare this to a truly PCIe connected device, be that an FPGA or a GPU, the advantage of doing this with a coherent model is that the path length through software is much shorter. What happens in an I/O model is really device drivers get involved, memory move instructions get involved until we hit the accelerator. And here it is just a delivery of a work packet in memory by the algorithm that runs on the processor core, and then a handoff to the accelerator that sits in the hardware or the GPU. So that reduces the path length of the software that's involved in handing over work to these accelerators by 40x. And that's the performance advantage that made us go after this CAPI model of direct accelerator connect. So that's one of the trends that connects things that we saw here at the conference and connects them to real system design in the industry as well. Obviously, FPGA acceleration in all its forms is a target for this capability, and the ease of programming in this case is a key part. Of course, mapping your algorithm to FPGA hardware is still a hard thing, so that's not taken away. We heard the Mellanox talk yesterday about RDMA. That's another entry path into this CAPI capability to go very directly into the memory address space and do RDMA from a NIC that's connected through the CAPI interface. Back to verification after this quick excursion here. Back to verification and to the constraints of logic design and their influences on verification. So when we look at what's driving RTL logic design, and RTL, remember, this was these strange language example that I showed you. If I'm a logic designer, what do I have to take into account? And this is where logic design really differs greatly from software programming. Software programming has its own constraints, its own performance constraints, but there's a whole world that opens up that to make logic design not programming. In fact, I get really a little miffed when people talk about RTL, writing RTL programs, because they might look a little bit like programs, but they really have to follow and deal with a lot of other constraints that a program per se doesn't have. So you couldn't take somebody that's a programmer and easily give them the task of writing efficient logic designs. So obviously, what we call mainline function and the performance, those are the primary categories when you think back about the flowchart in the beginning, where we say we break down the ISA to a microarchitecture and then we implement that. The first thoughts here are typically around these two topics, these two areas. But then there are other areas of concern that come in, and the flow here sort of indicates that these are all influences that go back and really shape the way that the logic is structured at this code level of the RTL code. So area, timing, and power, I said the function has to be mapped efficiently to two-dimensional physical structures. So that's expressed in these types of constraints. There's still a fairly tight loop here of saying, well, if I write something that is not implementable in hardware, time's up already, you lost, you have to go back to square zero. But then there's other, little bit further away constraints that come into play. Once we actually manufacture a chip coming out on a wafer out of the manufacturing line, we want to very efficiently check that what we manufactured doesn't have any manufacturing problems. This is the first step to establishing that we have a working chip. But all it deals, and this discipline is called design for test, all it deals with is finding bugs in the manufacturing process. Would not be found this way. They have to be found some other way. So in some ways, this is a completely additional constraint that goes into logic design. We have to put this in to be able to actually take a chip on a wafer and test it there. Then we go up sort of the semantic food chain. This design for debug. Remember I said we have to accept we find some bugs and bring up when we did the first round of manufacturing of this chip. Here is where this really matters. We put additional design components into these chips to actually make it possible that a chip that runs at 5 gigahertz can actually be debugged real time at the real clock speed. So trace and debug buses are on these things to allow us, this is almost like the recording that Robert was talking about this morning from the software side. This is doing real-time recording inside the hardware that we can then access when we find a functional bug. So we went from manufacturing to functional bugs here, and we pinpoint and we want to debug. Therefore, we need more information. So this is recording logic that goes in there. Has very little to do, is of course connected to, but has very little to do with the main objective here of our main function, which is the power instruction set architecture. Other areas are designed for security. So this is logic that prevents intrusion in any shape or form. Starts probably with the initial boot. You don't want somebody to override what is the prescribed method of booting one of those systems when it is in a data center, and security is really key there. And then we have design for reliability. This goes back to Bianca's talk yesterday of the soft error. It is one of the categories that we have here. There's also other reliability issues, reliability concerns that are being dealt with. And so we put real logic in that deals with these recoveries from these types of fails where you can, because you want to go as far as possible to recover from these types of problems. So key point of this chart here is there's a whole range of other concerns that go into the actual RTL logic design. And that makes this job really complicated. So design for reliability. There's a few other examples that are listed here. I took that out of a publicly available workbook for Power 8 as extensive use of ECC encoding, so we find and correct single bit errors when they occur. There's spare bit lanes on buses in case some connection goes wrong or gets flaky. You want to not replace parts. If the error gets more severe, we want to actually vacate a processor, vacate a core, and move the workload to another processor without the customer seeing that. Now, in the background, what happens there is that the machine could call home, right? It could say, hey, I have reliability issues here. Somebody should check this up. But the actual running job in the data center should absolutely not be disturbed. That's rule number one. Predictive configuration. So you can go further and further aggressive with this kind of defensive design that says, I want to recover from things that I see in real life and over a number of years in a data center. These are all considerations that go back into the logic of the original logic design. So back to our flow chart here, or our chart of additional concerns. We have a name here, and the industry has a name for this type of logic that's in addition to this mainline function. So it's the mainline function is hard already, physical constraints, mapping this into something that really works at a clock frequency of 5 gigahertz is important. But then we have this design for manufacturing test. What do? We put intrusive logic structures into the design to allow us to find these after manufacturing. Design for debug. Again, we're having intrusive logic structures to pinpoint functional errors. The 2 plus 2 is 5. Probably not that trivial, but something to think of this way. And we want to trigger an event on the outside of the chip that lets us debug and take the instrumentation collected data out of the chip to do the debug. Design for reliability. Again, this is intrusive logic structures to pinpoint and repair those soft errors. So all of these now collide with the functional design. When we said verification is hard and it's this 30 to 70% type problem on a design project like this, verification becomes harder through this because we are putting all these additional intrusive logic structures and putting them around and into the mainline function structure. So what you would think is a very clean modular description becomes corroded by these types of effects. Here's an example out of a workbook that says we found ways, and others in this design space have found that too. We found ways where we now take this intrusive logic structure and we put structure into that intrusion with the special IOs, special buses. You don't have to understand any of this, but basically what you see is here's a processor core and there's modules that deal with this, what I call pervasive function, but the endpoints of this pervasive function really still goes all the way into the functional modules of the original design. That's unavoidable, that's by definition. And so when we go and implement a piece of RTL code, that RTL code actually is a merge of all these design concerns together. And now you can see that creates a problem for verification. And this is where a couple of more pictures will probably help, but I'll go quickly over them. The multiple reasons, and we saw most of them here for driving cross-cutting structures into the RTL. One of the key ones, as an example, is that physical proximity has the highest priority. One of the key constraints is be able to run at 5 gigahertz. 5 gigahertz means distances have to be as short as possible. So if I have a logic structure that has these orange clouds as functional, but I need to, for these more greenish or turquoise logic structures, I have to go from this place to this place up here. I have to go through somebody's module. So I'm intruding the modularity of this module. And if this is what I'm actually putting on the chip physically as the geometry, I have a collision of two original modules. So why is this problem for verification? It actually drives the number of bugs up. Right? We've seen this on the precursor of Power 8. We've seen this where at some point the negotiations that went on between the module owners that had to host logic from other modules crossing geometry boundaries, where these cost us 3 months of time, of churn, of instability of the design model, and more bugs ultimately. And the ownership is that's one of the bigger issues, is defocused because the person here that owns the orange module doesn't really care about and doesn't understand what's this logic function that all of a sudden gets hidden in my module. So this is where the idea of aspect-oriented design came in, and we looked at how does software deal with cases like this. As a quick reference to a keynote from the Design Automation Conference. This is now 3 years ago, where we first sort of launched the idea to the rest of the industry to say, this is today's world where the poor logic designer has all these requirements from these subject matter experts. Like the design for manufacturing guy comes and says, hey, you have to put this type of logic into your design. What would happen? Would the world not be much better if we had these expert designers work in parallel and we could actually merge the different aspects of this design? So that was the first visualization of a larger vision we had here. When you go, for folks that are not familiar with aspect-oriented programming, you go back to the first principles of what led people to invent aspect-oriented programming. There's a picture directly out of Wikipedia here. Is a similar issue, similar set of issues. For the mainline function of your software application, you construct classes. And that's a well-designed hierarchy that defines partitions of things that are not enmeshed with each other. Module boundaries is the divide and conquer formula of success. But then you have cross-cutting aspects. Just like I showed you in the hardware, cross-cutting aspects of persistence, transactions, security, logging. Logging is the typical example you read in one of those books about aspect-oriented programming, where you say, let's imagine every method call in your class needs to call a logging function. You don't want to go into the class definition and pollute that with all these calls to the logging function. The idea is to separate aspects of concern and separate them at the source code level and create the cohesion of code in one single place. And that's exactly what we're trying to do with hardware. Also, candidate aspects, we talked about them before. I don't have to repeat this. Now, there's a quick sidebar here that says, why is this really a problem? Couldn't the creation of some of these aspects be fully automated? For example, the design for manufacturing. And so for some designs that actually works, where you say, hey, I have this program, call it the silicon compiler, call it whatever you want, or logic synthesis tool that actually sprays the logic into the designer specified logic that collects data that says this is manufacturing okay, this chip coming back. For a lot of designs that does not work, and the biggest issue is it takes the assumption that you can fully automate this, takes away the complete control from the logic designer. And so our goal for aspect-oriented RTL design was to have these aspects be defined at the RTL level, and the output of the aspect weaving, when you take the different pieces together, the output of the aspect weaving stays at the RTL level. So it's controllable, it can be still human readable, and the sources that get woven together are created by humans if they need to be. So rather than having the subject matter experts all mess in this one mainline function design, what this does is in our lingo now, we started to invent this methodology on the fly. We said, okay, there's a set of recipe files that the design for test designer specifies. The pervasive recipe file, let's say this is a debug and trace logic instrumentation that goes in, that's specified on the side, and then there's this program that inserts and weaves these together, and out comes still RTL source that's still available for simulation. But what I can do now is I can take modules that are of other concern, of other aspects of the design, and I can verify them standalone without having them enmeshed completely. This is where we start today, at this level. Here we can start at the upper level. So we called our project Morph for the obvious reasons. So it's a toolkit that actually is very much a compiler-based toolkit that takes allows the separation of aspects and allows to do them mostly at the RTL level, and then weaves these aspects together and creates the RTL output that then goes into the physical implementation process. One example, quickly, in the interest of time. One example here is what we call Morph Hierarchy, that deals with one specific aspect separation that is of high interest and is actually being used in Power 9 now in production, this technique. There are reasons and constraints to group design elements along hierarchical boundaries for different modularity granularities. Based on functional cohesion is one, geographic adjacency would be the other. And the larger these chips still get, and they get larger by the amount of logic that's on those chips, this is becoming an increasing problem. So in pictures, what Morph Hierarchy does is it allows the separation of the functional modules. So this would be one unit, this would be another functional unit from our prior little graphical example. There would be a recipe file that says, take these following objects in the hierarchy and merge them together differently for the purpose of physical layout and physical adjacency where that matters. Now the key is this is not a fully automated process, just like SIMD this morning wasn't a fully automated process. The key is that there's a human here that understands very much something about the physical layout of the chip and has an influence to write this recipe that says, take these blocks and put them together like this. Now we run verification on this level. We don't run verification on this level anymore. This has to be correct by construction, which actually is proven by another set of equivalence proofs using formal technology, formal methods there. Just very quickly, to show it on a more complex example, using our pervasive logic example here, in the logical hierarchy, so this is what the logic designer deals with, what the verification engineer deals with, they can focus on the pervasive logic altogether, and they can create a test bench around this at this level and not worry about that for true physical constraint reasons, this pervasive logic has to be spread out over the chip hierarchy like this. So that would be the hierarchy view of this. Or if you will, in the physical view, those pervasive pieces of logic would be, if you took the logical hierarchy, literally, those pieces would be together, and that would be devastating for reaching the 5 gigahertz. They actually have to be placed and distributed in the hierarchy like this. And so what we now have is 2 hierarchies that are connected with each other through the Morph Hier process and through the recipe file. It's a classic application of aspect separation and then weaving together where needed. So in conclusion, we've seen this spark of this idea coming from the software world, and we can see this really be applied to hardware design in a fundamental way and very productively now in real time and in real life projects. It lets us substantially untangle these artifacts of logic design, which is a productivity increase and an efficiency for verification increase. We have developed a bunch of aspect-oriented apps around this using our own imagination, our own constraints. I want to mention that the rest of the industry is moving in a very similar direction because, of course, unsurprisingly, those constraints are there as well. They might not call it, they might not call it aspect-oriented design, but there's a number of companies out there, specifically the last 2 here in the design automation space, that have very, very similar approaches for the very similar reasons. So this is an emerging theme, and I have a feeling that aspect orientation will be more successful in hardware than it ever was in software. So with that, thanks for your attention, and be glad to answer a couple questions.